Hello friends, Dr.K.GUNASUNDARI, Assistant Professor of Chemistry from A.D.M.COLLEGE for Women, Nagapattinam. We are going to discuss about stereochemistry. We shall see what is meant by stereoisomers first. Two or more compounds with same molecular and structural formula but different spatial arrangements of atoms or groups are termed as stereoisomers. Such a phenomenon is known as stereoisomers. Enantiomers. What are enantiomers? Enantiomers are stereoisomers that have identical physical properties but different dissociation, direction of rotation of the plane polarized light. They have identical chemical properties but different optical activity. They are resulted from chirality. They differ from one another only in the way of atoms arranged around the chiral center. Say for example, 2-methyl-1-butanol have two enantiomers which differs only in the sign of rotation. And another example is glucose. Plus glucose and minus glucose we used to say. Coming on to diastereomers. Stereoisomers that are not mirror images of each other are called diastereomers. Diastereomers may result from chirality or from cis-trans isomers. Chiral systems may be enantiomeric or diastereomeric, whereas cis-trans isomers are always diastereomeric and never enantiomeric. They differ in the chemical and physical and optical properties also. They have different specific rotation with the same or opposite signs of rotation also. They may also be optically inactive. They differ in melting and boiling points. They can be separated by fractional distillation itself and also by chromatographic techniques. They differ in the absorption and adsorption characteristics. Say for example 2,3-dibromopentane. Coming on to dextrorotatory molecule. What is meant by dextrorotatory molecule? A dextrorotatory molecule rotates the plane polarized light towards the right. Levorotatory molecule is one which rotates the plane polarized light towards the left. And meso structures, meso compounds which are superimposable over their mirror images. They are called meso structures. They have plane of symmetry. They also have chiral center, but they are optically inactive. So three things we have seen: dextrorotatory, levorotatory and meso molecules. So dextrorotatory molecule, there is plus tartaric acid having given as an example. Levorotatory molecule, there is minus tartaric acid, and this one meso tartaric acid is also given as an example for the three categories. Erythro and trio molecules. What are erythro and trio molecules? We shall see. Molecules with the two different chiral centers, not necessarily an adjacent carbon atoms, are often designated by the prefix trio and erythro molecule. Erythro molecule, the molecules with the two identical groups on same side of the carbon chain in their Fischer projection formula are termed as erythro molecules. Trio molecules, the molecules with the two identical or similar groups on opposite sides of the carbon chain in their Fischer projection formula are termed as erythro molecules. So racemic mixture. When an optically active compound is synthesized in the laboratory, the dextro and levo varieties are obtained in equal amounts and a racemic mixture results. The separation of the racemic mixture into an enantiomorphs is called resolution. So racemization. Next step. So racemic mixture means all the enantiomorphs, that is dextrorotatory and levorotatory molecules mixed together is called as a racemic mixture. Whenever we produce something, some organic molecules, we come to know about the racemic mixture being produced as a result. What is this racemization? 50-50 mixture of dextro and levorotatory isomers of a compound are called racemic mixtures, and they are optically inactive. When a solution of optically active plus tartaric acid in water is heated, it is transformed completely into its inactive mixture of racemic mixture. That is, in situ, mesotartaric acid is also being synthesized due to heating. The phenomenon of spontaneous production of levo variety from the dextro variety and vice versa to produce racemic mixture is called racemization. What are the methods of racemization? We shall see now. The action of heat, the rise of temperature always favors racemization. Example, lactic acid, amyl alcohol, tartaric acid gives a racemic mixture on heating. Second one, treatment with chemical reagents. Any chemical substances undergo racemization when treated with suitable chemical reagents. Say for example, mandelic acid. When treated with hydrobromic acid, it forms plus and minus bromo acids. Auto-racemization also we may expect. In some cases, special cases, racemization occurs spontaneously at room temperature without any increase of temperature, without any reagents being applied. Spontaneous racemization also occurs, that is called as auto-racemization. Example, dimethyl bromosuccinate isomerizes at room temperature. We are going to see about the elements of symmetry. What are the three elements of symmetry? Main thing. So, a symmetry, that is similar thing. See, center of symmetry. A center of symmetry is an imaginary point in a molecule such that if a line is drawn from any group of the molecule to that point and then extended to an equal distance beyond that point, it meets the mirror of the original group, that is center of symmetry. Next comes plane of symmetry. A plane of symmetry is a plane which divides, an imaginary plane which divides the object into two equal identical halves is called the plane of symmetry. Next, coming to the axis of symmetry, we know three axes generally as x-axis, y-axis and z-axis. Likewise, n-fold axis are there. An n-fold axis of symmetry is an imaginary axis such that when structure possessing such an axis is rotated through an angle 2 pi by n, it is similar, it is producing some similar structure. Okay, so that is axis of symmetry. What is meant by these are the three symmetrical elements, that is center of symmetry, axis of symmetry and plane of symmetry. Coming on to the asymmetric molecules, the term asymmetry denotes absence of any symmetry. An object or molecule in asymmetric mode, if it has no element of symmetry, if a molecule does not have any elements of symmetry, it is said to be asymmetric molecule. All the asymmetric molecules are said to be chiral molecule because they produce non-superimposable mirror images. This symmetry, a chiral molecule having only one axis of rotation, that is only one element of symmetry, that is axis of rotation alone, is present when such a molecule is called dissymmetric. Such molecule may be optically active molecule also. That is interesting. So next coming on to the optical isomerism. Interesting thing. Optical isomers or the isomers which resemble one another in their chemical reactions, their physical properties are similar but they differ only in their optical properties. What is this optical properties? That is behavior towards polarized light, plane polarized light. Such a phenomenon is known as optical isomerism. Optical isomerism is due to different spatial arrangements of atoms or four atoms around a single molecule. Four atoms or groups, if they are attached to the same carbon, if all the four atoms or groups are different attached to the same carbon, they are supposed to be optically active molecule. If such molecule is exposed to plane polarized light, then what happens? They may turn the plane polarized light towards the right, that is called as dextrorotatory molecule. If an optically active molecule turns the plane of plane polarized light towards the left, they are called as levorotatory molecule. So from a light source, a light emerging from a light source, when it is passed to one polarizer, it produces a plane polarized light, that is a light which propagates only in one direction. When such plane polarized light is subjected to an object, that is optically active object, if that optically object turns that plane of plane polarized light, we are able to identify dextrorotatory or levorotatory molecule. So instrumentation of polarimetry is also like this. Next. We are going to see the optical isomerism with few examples like lactic acid, 2-butanol, glyceraldehyde and 2-bromobutanol. These molecules possess optical activity. We can express them in few terms, that is D and L notation also. Since it is convenient to designate the configuration of a molecule by a symbol, a system involving the letters D and L are being adapted for this purpose. Say for example, D-glyceric acid, D-lactic acid, L-alanine, L-phenylalanine, D-glyceraldehyde, L-glyceraldehyde. Likewise, we used to use the notations. How to use these notations we shall see. Here, certain rules are there. Say for example, that is a D, a dextro, L means levo. These things we have seen already. Coming on to a few other notations, that is RS notation of the optical isomers. We have to follow certain sequence and rules. What are the rules? We have to see. Rule 1. When four different atoms are attached to the chiral carbon atom, priority depends upon the atomic number, with the atom of higher atomic number getting higher priority. If the atoms or the isotopes of the same element, atoms of higher mass number is given the higher priority. Say for example, in chloroiodomethane, sulfonic acid, and other things. The sequence comes like this. Okay, so we have to go with the atomic number, and then if the same elements isotopes means the elements with same atomic number means we have to go with the atomic mass also. Rule 2. If two atoms attached to the chiral carbon means what? A carbon which is attached to 4 different groups or atoms, that is said to be chiral carbon. So coming to the rule 2, if two atoms attached to the chiral carbon atom are the same, then we have to go for the another priority order. In such cases, compare the atoms attached to each of these first atoms. The relative priority like methyl group, ethyl group is decided as follows. In secondary butyl chloride, we have to give the priority likewise. Chlorine first because atomic mass of chlorine is higher, so chlorine first, then ethyl group, then methyl group, and then comes the hydrogen. Likewise, we have to give the priority order. Okay. In 2-methyl pentane also the same thing happens. Rule 3, that is a doubly bonded or triply bonded atom A is there means we have to consider that a is represented, and if it is doubly bonded A means we have to consider that 2 equivalent bonds are being connected to A. Likewise, if out of that is say for example, if a triply bonded atom is there means we have to consider it as the 3 different bonded atoms. Likewise, conformational isomers. Next, coming on to conformational isomers. An infinite number of atomic arrangements are possible for a single molecule, depending upon the angle through which we can rotate a particular group. And this angle of rotation is called dihedral angle. Different spatial arrangements of a single molecule that are generated by rotating a molecule about a single bond are called conformational isomers. Such phenomenon is called conformational isomerism. 2 extreme arrangements of the atoms or conformations of ethane are being discussed here. They are called eclipsed and staggered conformations. In eclipsed conformations, the 3 hydrogen atoms attached to the front carbon are exactly in front of those attached to the back carbon atom. So they are aligned together. All the bonds are being aligned in a straight line. In staggered conformations, all the 6 hydrogen atoms are clearly seen and appear symmetrically situated at maximum possible distances. The staggered form has been found to be more stable than the eclipsed form by 12.6 kilojoules per mole. So this is the example, that is eclipsed form and staggered form. Since eclipsed form is highly rigid and it have some strain in its structure, so it has high energy and a low stability. But in staggered form, all the bonds are free enough. Staggered form, they are highly stable. So coming on to what are the notations, what are the pictorial representations which we can use in the paper in order to understand, in order to visualize the molecule in 3-dimensional way. First one is Sahar's drawing. Sahar's drawing, the 2 carbon atoms under considerations are taken first as 2 points where 4 lines intersect, and the remaining groups are attached to the 6 free ends. The bond linking these 2 carbon atoms is considered to be the plane of paper. The remaining lines, that is bonds, projects above the plane and below the plane also. And therefore, there is a free rotation about the carbon-carbon bond, and the 3 groups attached to the front atom may be rotated clockwise or anti-clockwise with respect to the groups attached to the rear atom. For example, 2 conformations of ethane, that is eclipsed and staggered form, are shown below. Okay, Newman projection. In a Newman projection, what we have to do? That is, we have to view a Newman projection. The nearer carbon atom, it has been represented by a point, while the bond linking the 3 carbon groups attached to this carbon atom are represented by 3 lines radiating from this point. The carbon atom situated far away is represented by a circle, and its 3 bonds are represented by 3 lines radiating from the edges of the circle itself. In this way, we have to think. That is, a small circle represents the front carbon and the largest circle representing the rear or backward carbon. We have to imagine in that way. And we can also understand that Sahar's projections can be represented as Newman, and Newman projection formula can also be represented in terms of Sahar's projection formula. Since there is a free rotation about the carbon-carbon single bond, the Newman projection formula just represents one of many stereoisomeric forms. These projections will show that rotation of the front methyl group by 600 above the CC axis, that is carbon-carbon bond, converts the staggered conformation into the eclipsed group. 60 degree about Say for example, we have to rotate the front carbon 60 degree so that it gets converted from one form to another. Staggered can be converted into eclipse if you turn that front carbon about 60 degree. If you turn the backward carbon to 60 degree, again it will get converted into the other form. Likewise, if you keep one carbon stagnant and another carbon, if you turn to 60 degree, rotate it to 60 degree, then the whole molecule structure gets different. There is staggered to eclipse form we can arrive. So thus every time a staggered form is reached, potential energy of ethane decreases to minimum and again increases to maximum when eclipse to conformation is attained. A plot of potential energy of the ethane versus degree of rotation of the front methyl group alone for one complete rotation, there is 360 degree about CC bond is shown below. Thus, there is an energy barrier also, that is 12.6 kilojoules per mole in passing from one staggered form to another form. So, this is the graph and the pictures which arrives at the transformation from staggered form to eclipse, again from eclipse to staggered form, and goes on like that. Coming on to Fisher projection formula. How to use this projection formula? In Fisher projection formula, thick horizontal lines represents the bonds directed towards the viewer. The dotted lines represents the bonds away from the viewer. The intersection of the horizontal and vertical lines represents the chiral center, and the horizontal lines represents the bonds directed towards the viewer, and the vertical lines represents the bonds directed away from the viewer. So the Fisher projection formula retains their configuration on rotation by 180 degree within the paper itself. So we can see the example D-glucose and L-glucose, which are represented by Fisher projection formula. Conformations of cyclohexane. Coming on to this interesting topic, the stereochemistry of cyclohexane is very, very important and quite interesting. Since the HCH bond, HCC bond, the HCC bond angle in the planar hexagon ring is 60 degree. It is much deviated from the tetrahedral angle, that is 109.28 degree. Predicts the cyclohexane molecule to be highly strained and the cyclohexane molecule to be very unstable. But experimentally it is being proved that cyclohexane is very stable compound. How come it is possible? In 1890, Sachet pointed out that two Packard, that is non-planar models of cyclohexane, that was quite interesting, that could be constructed in such a way that the valency bonds of all the carbon atoms are tetrahedral and each and every bond angle, that is 109.28 degree, and were free from strain, totally free from strain. And if we plot the potential energy curve of cyclohexane as a function of the dihedral angle, we get the curve like that. One of the Packard hexagon models is called a chair form, which is rigid, and the other Packard form is called a boat form. During the transformations, while flipping from chair form to boat form and from boat form to chair form, we get intermediate conformations also. They are called as twist boat form or skew boat form. So these are all the three pictures which depicts the chair form, boat form, and twist or skew boat form. Of these three pictures, the most stable one is the chair conformation, because the restriction, steric hindrance are much more lesser when compared to the other two forms. So what are the two types of bonds present in this chair conformation? Axial bonds and equatorial bonds. Axial bonds, the bonds parallel to the axis of symmetry of the molecule, are called axial bonds. Equatorial bonds, while the bonds which makes an angle 109.28 degree with the plane of the ring, they are called as equatorial bonds. Each carbon has one axial bond and one equatorial bond. On the whole, 6 carbon atoms are there, we know, in cyclohexane. So totally 6 equatorial bonds and 6 axial bonds are there in cyclohexane. Conformation analysis of substituted cyclohexane. So if you have some substitutions there in the cyclohexane, which place is more favorable? Since substituted cyclohexane can exist in two forms, that is cis form and trans form. Since cis means that is the two similar groups present on same side. Trans means similar groups on opposite sides, that is cis and trans isomers we know. So substituted cyclohexane means we can expect two forms, that is cis and trans. When cyclohexane is substituted, the most stable conformation is the one which is having the substituent occupying equatorial position, not the axial position. Equatorial position is most favored in the substituted benzene, cyclohexane. Say for example, tertiary butyl cyclohexane, that is equatorial position being substituted means it is highly stable when compared to the axial position. So till now we have seen a lot of things regarding stereoisomerism, optical activity, chirality and other things. So we shall have another beautiful class. Until then, thank you so much.